Hello everyone. I'm taking you to space again tonight. Recently we went to Mars to explore this planet and the concept of terraforming. Then to the Jovian system, that is to say Jupiter, its rings and its moons. Tonight we will go even farther. We will cross the orbit of Saturn and visit the seventh and eighth planets from the Sun, Uranus and Neptune. These two are called ice giants. We will see why, and I'll tell you also about the theories, the models that explain the formation of the solar system and these planets, and their differences in size, composition, or orbits. We will also take a look at their moons and dive through the atmospheres of these two planets to see what there could be inside. This is going to be a long journey, so make yourself comfortable. You can sit or lie down, eyes opened or closed, it's up to you. But as always, you can follow and understand everything just by listening. And don't hesitate to let yourself drift and fall asleep. You can always return to the journey where you left it, with the timestamps in the first comment pinned under this video. There are also links in the same comment if you would rather listen to my stories on Spotify and other audio streaming platforms. It's the same as YouTube, but it can be more comfortable if you want your screen to stay dark, or if you prefer stories without sound effects during or after I'm done talking. And if you feel like supporting this channel, there is a link to my Patreon page too, where you can also download everything I do, get more updates, and the stories as podcasts. It costs what you decide, from $1, £1 or €1 a month. And now, let's get ready for the journey. I'm sure that once again there is tension in your shoulders and your neck that you live with without noticing. You can now gently release it and try to remember to do it sometimes during the day too. It cannot hurt. Then do the same along your arms, all the way to your hands and your fingers. And now your legs, including feet and toes. You can yawn a little, and now that I have mentioned it, it is going to be hard to repress. But that's a good thing. Just think about the quietness, the peacefulness of space, and the beauty of thousands of stars. You are perfectly safe on this journey, and it begins right now. How far are Uranus and Neptune from us on Earth? You remember from our previous space stories that there is an unit that is useful to figure out distances in space, the astronomical unit. It was defined, roughly, as the equivalent of the distance from the Sun to the Earth, which is about 150 million kilometers, 93 million miles. light takes about 8 minutes to travel this distance, and the astronomical unit is convenient to compare distances between the orbits of planets. So, the Sun to Earth distance is 1 astronomical unit, the Sun to Mars 1.5 units, Jupiter, which is the 5th planet from the Sun, is at a bit more than 5 astronomical units. Saturn, the 6th planet, is almost twice as far as Jupiter, 9.5 astronomical units. But to reach Uranus, we need to double that distance again, about 19 astronomical units. 19 is like a middle point, because the orbit is not a perfect circle, it is slightly elliptical. At its closest, the distance is a bit more than 18 astronomical units, and at its farthest, a bit more than 20. But a good order of magnitude to bear in mind is that Uranus is 19 times farther from the Sun than Earth, and Neptune is 30 times farther. At this distance, light and heat from the Sun take more time to reach them, and there is much less. They don't have a solid, rocky surface, as you know, so we cannot really say that they have a cold surface. But the upper layers of these planets are extraordinarily cold. We will see how cold when we approach them. The first close images we got from Uranus are not very old. They were taken by a probe, Voyager 2, in 1986, and they revealed a planet that looks almost featureless, without the kind of cloud bands and storms that are observed on other giant gas planets. Neptune looks more animated, but both planets have conditions in their upper layers that are some of the most extreme in the solar system. So first, let's talk about what they are made of and why they are called ice giants. Until the 1940s, astronomers distinguished 2 main types of planets in the solar system. The rocky ones, with a solid surface, like Mercury, Venus, Earth and Mars, and gas planets, which are bigger and do not have a clearly defined surface, because they are made of gas in various layers, denser and denser as you move towards the center. And their core is believed to be made of rock and metal, around which gas has accumulated and stays, kept together by gravitation. There were 4 gas planets: Jupiter, Saturn, Uranus and Neptune. It was assumed that their composition was more or less similar, mainly hydrogen and helium, the 2 most abundant elements in the solar system, and most probably in the universe in general. They are the simplest, the smallest types of atoms. There are heavier elements, dozens of them, including some that are also relatively abundant, like oxygen, iron, and carbon. But it is believed that these elements are mostly younger than hydrogen. Like other heavier atoms, they would tend to form in stars when they approach the end of their lives. You know that the fuel of stars is hydrogen. Inside them, hydrogen is exposed to such extreme conditions that fusion happens. Atom cores combine to form heavier atoms, mainly helium, for most of a star's life. But when the end of a star nears, because it has consumed a large part of its hydrogen reserves, which takes hundreds of millions of years, billions of years in the case of a star like the Sun, the star starts consuming helium, and heavier and heavier elements are formed. It is believed that this is how these heavy elements appear, all the way to big atoms with dozens of particles, like gold or uranium. And then, when a star dies, it becomes gigantic, it explodes in a supernova, which would disperse these elements, and they would become available to form new systems. Our system is much younger than the estimated age of the universe. I told you about all that in the video about cosmology. I put the link in the description. So if these theories about the universe, stars, and the formation of star systems are accurate, it is not surprising that these heavier atoms are actually present in our solar system, either alone or combined with others, in compounds like ammonia, carbon dioxide, sulfur dioxide, or water. But still, most of the solar system, if we take into account the Sun itself and all the planets, is still mostly hydrogen and to a lesser extent helium. And as it happens, these are also the main components of gas planets like Jupiter and Saturn. They probably have rocks and metals in their core, and they have other compounds in small quantities in their various layers. But this isn't much in proportion. So, until about the 1940s, it was assumed that Uranus and Neptune, because they were giant planets with no defined surfaces like Jupiter and Saturn, had a similar composition. To put figures on this, it is estimated that Jupiter and Saturn are more than 90% hydrogen and helium. But it appeared through spectroscopy and estimates of their mass relative to their size, and later measurements sent by probes, that no, Uranus and Neptune were quite different in their composition. Only about 20% of hydrogen and helium by mass, and a lot of compounds like water, hydrocarbons, and ammonia. These different compounds are called ices in astrophysics and planetary science, because when they are independent from a larger body, like a planet, and at a sufficient distance from a star, they are generally found frozen as solids. On Earth, when we hear the term ice, we think about water ice, whereas in astronomy, ice refers to a broad range of compounds that includes water and various more. These compounds have in common that they freeze above or near 100 kelvins at Earth's surface pressure. They include water, which freezes at 273 Kelvin, which is 0 degrees Celsius. The Kelvin scale is similar to the Celsius scale, except it begins at 0, the lowest possible temperature, whereas the Celsius scale begins at minus 273. So water freezes at 273 Kelvin and 0 degrees Celsius. Ammonia freezes at 195 Kelvin, that's minus 78 degrees Celsius, or methane freezes at 91 Kelvin, minus 182 Celsius. These elements make the majority in mass of Uranus and Neptune. And this is the scientific reason why they are called ice giants. But it can be a bit misleading, because when we hear ice giant, we may think about a planet with a hard surface, which they are not, or one with blocks of ice floating in its atmosphere, which they don't have either. The term ice refers to the compounds they are made of, not the state they are in, because, as we will see, these compounds are no longer solid. They might have been when the planets formed, but they no longer are. The term was needed to differentiate these planets from gas giants, like Jupiter, because their composition and formation history were quite different, and the term ice giant sounded appropriate, which is why it was adopted over the past 40 years. Now, a good question is why some planets are rocky, others are made of hydrogen and helium, and others of ammonia, water, and methane. And why is there an apparent order in the solar system with 4 rocky planets near the center of the system, then 2 gas giants made of hydrogen that happen to be the 2 biggest planets, Jupiter and Saturn, and after them 2 ice giants that are in between rocky planets and gas giants in terms of size and mass. To try answering this, we need to talk about the theories of planet formation. One thing that makes the formation of planets harder to research is that we only have one system at our disposal, ours, and there are not that many planets in it. Only 8 bodies are considered massive enough to be classified as planets, plus a few smaller bodies like Ceres or Pluto, dwarf planets, but that's not many. The starting point of a star system is something relatively uncontroversial among astrophysicists at this point. It is still theoretical, but it is backed by a lot of observations from the chemical composition of planets to their orbits, the laws of gravitation, and even, since 2018, the direct and confirmed observation of a star system in formation around a newly formed star called HL Tauri, 450 light-years away from us. It is far, but not that much at the scale of the galaxy. It is believed that a star system begins to form when enough matter, gas and dust, coming from a nebula concentrates in a smaller space. A nebula is an immense cloud of matter floating in space. There are several in our galaxy. And the main force behind the formation of a star system is gravitation. In this region of space, this matter in suspension tends to take the shape of a large disk that rotates on itself. For this rotation to begin, an initial impulsion is needed. It is believed that supernovas, the final explosions of stars, could provide it, because they send a shock wave in space. As this disk rotates, matter tends to concentrate in the center faster and faster because the mass at the center increases, absorbing more and more matter. And when the mass becomes critical, big enough for pressure at its center to ignite fusion, it becomes a star. Typically, this new star goes through a short period of growth, during which it absorbs most of the disk. In the case of the solar system, more than 99% of it. We know that there are systems with several stars, 2 or even 3, of different sizes. So there is not a single possible accretion model, accretion process, but it seems the single star model, like our system, is the most frequent one. In any case, this doesn't let much matter available, but still enough to form several planets that concentrate the rest of the protoplanetary disk, what the star hasn't swallowed. This protoplanetary or accretion disk is the basis of planetary formation models. But then there are theories that explain differently the specifics of planets' formation, and ice giants are a bit of a problem here, because their existence appeared as a challenge to existing theories when their composition was discovered. The formation of rocky planets like Earth and also gas giants like Jupiter, this is not very controversial. They are widely understood to have formed through millions of years of collisions of smaller rocky bodies within the protoplanetary disk, until one larger planet remains on its orbit, having cleaned up the orbit of all other bodies. But why do some of these planets become gas giants instead of terrestrial planets? It would be because they would have formed bigger solid cores, around 10 times the Earth's mass, and so with a more powerful gravitational pull, they would have also acquired, by accretion, an envelope of gas. Based on the observation that in the solar system, rocky planets are closer to the star, and gas giants farther from it, it is supposed that the distance from the star also helps retain gas. So, for a long time, it was believed that gas giants had to form relatively far from the star, from the center of a system, whereas rocky planets could be more central. Actually, they could theoretically be distributed in a large part of the protoplanetary disk, but they would tend to become satellites, moons, of gas giants if they were close to their orbits. But in the past 2 or 3 decades, this theory, this assumption, has been questioned by many observations made outside our system, with plenty of exoplanets and other star systems. It appeared that there could be large gas planets, exoplanets, orbiting close to their star, and with a very short orbital period. That is to say, they orbit quickly around the star, as little as a few days, to compare with an entire year for Earth or 12 years for Jupiter. When these gas giants that are close to their star were discovered, they were called hot Jupiter, hot because they are close to the star. And clearly their existence raised a challenge to existing theories about gas giants. These are the easiest exoplanets to discover, because they are big and they are close to their stars, which makes them stand out. They are much easier to spot, and there are plenty of hot Jupiters. So the theories were revisited. The prevalent view about hot Jupiters at this point is that they probably form far from their star, and then they migrate closer to it. The migration could be progressive due to an imbalance in the system until they find a stable orbit close to the star, or it could happen due to a collision that suddenly modifies their trajectory in space. An alternate hypothesis is that they form in situ, close to the star, maybe due to a particularly big solid core that has a lot of gravitational pull. The truth is that this remains an open question at this point. But returning to ice giants, the problem they raise is that these models that work well with terrestrial planets or giants like Jupiter have a very hard time explaining the formation of these big planets so far from the star. Why is that? Accretion of a rocky core requires collisions, plenty of them, and the formation of a protoplanet that progressively cleans up its orbit by absorbing everything on it. So at the start, the protoplanets are fairly small, and a theoretical problem here is that given their distance from the star, a protoplanet forming on the orbits of Uranus or Neptune should have been expelled, when they were smaller, from the solar system. Based on the laws of gravitation, it is logical that a planet like Jupiter or Saturn stays within the system. They are at 5 and 9.5 astronomical units from the star. But the further you are from the Sun, the less you are bound to the system by gravitation. The force decreases with distance, and at 20 astronomical units like Uranus, or even more, 30 like Neptune, with the accelerating effects of Jupiter and Saturn, the protoplanets would have surpassed the escape velocity. That is to say, they would have traveled fast enough in space to overcome the Sun's pull, and they would have left the solar system. Or they should have been pulled and absorbed by Jupiter and Saturn, or turned into comets, before fully forming. But obviously it didn't happen, because they are here. But a planet forming by collision at 20 astronomical units or more from the Sun, and staying there on a stable orbit, is something that formation models have a hard time explaining. And to make things even more complicated, it seems that Uranus and Neptune are no exceptions. Plenty of exoplanets that have been discovered in other systems are candidates to be ice giants. So what could have happened? A first possibility is that they would have migrated after their formation, like possibly hot Jupiters do. They would have started to form somewhere between the orbits of Jupiter and Saturn, 5 to 10 astronomical units from the Sun, and then changed orbit at a time when their sizes and speed were sufficient to keep them bound to the solar system. It is not precisely explained how. There are different theories about this outward migration. It could be, for example, due to close encounters with Jupiter or Saturn that would have expelled them to another orbit. Or another possibility is that they formed differently near their current orbit, but in that case it couldn't be through collisions. An alternative that could work, theoretically, would be that they formed due to instability in parts of the protoplanetary disk. There could have existed regions of slightly higher density in the disk that could lead to the formation of clumps of matter that eventually collapsed due to gravitation to form a planet. Models suggest that a disk with a bit of instability could yield protoplanets between 10 and 30 astronomical units from the star, and both ice giants of the solar system are within this range. So, at this point, the formation of Uranus and Neptune is explainable. The thing we don't know is what mechanism, what process happened, because these processes may have been very different. But we are now at 19 astronomical units from the Sun, approaching Uranus. Even though it is way smaller than Jupiter and Saturn, it was observed from Earth centuries ago, maybe as early as the antiquity. But for a long time it was mistaken for a star or a comet, until the late 18th century, when several astronomers realized that due to its movement it couldn't be a star and had to be a planet beyond Saturn. Uranus is about 19 times farther from the Sun than Earth, as we said, and it is also slower on its orbit, so it takes much more time to complete a revolution, 84 years. Actually, since it was identified as a planet in 1781, it has made less than 3 complete orbits. I also told you earlier that it received much less sunlight than us, due to the distance. The intensity of sunlight varies inversely with the square of distance. In other words, it decreases faster and faster as you move away from the Sun. And so at 19 or 20 astronomical units, depending on where the planet is on its elliptical orbit, it receives 400 times less light than Earth. In other words, Uranus travels in space in the dark, and if we looked at the Sun from it, the Sun would be a small point in the distance, not the big and bright light we see from Earth during daytime. Uranus has several moons, 27 have been identified, and we will explore the biggest of them, Titania. But first, let's start traveling inside the planet, from its atmosphere to its core. What we call atmosphere here is just the envelope of gas, because there is no well-defined solid surface. So the atmosphere has been defined as the region that was accessible to remote sensing, up to 100 bar of pressure. That is still hundreds of kilometers or miles within the planet. We saw earlier that the pictures taken by Voyager 2 or telescopes with a lower definition suggest a peaceful, quiet, featureless planet that looks pale blue-green. This is due to the composition of the atmosphere that absorbs red light, but this may be misleading. The planet's atmosphere is very active, and for short periods of time, it happened for 2 months in 2004, for example, large clouds can appear in the atmosphere and spectacular storms can take place. Record-breaking winds have been observed at more than 500 miles per hour. That's more than 800 kilometers per hour. And even though the climate is not very well known, it seems it is subject to big variations. Since the 1990s, and thanks to imaging with higher definition and under different types of light, a lot of clouds and atmospheric phenomena have been discovered. In this atmosphere there is mainly hydrogen and helium. You remember they account for an estimated 20% of the planet's mass, and these elements are thought to be absent from the denser parts of the planet. The third element, that would account for a bit more than 2% of the atmosphere, would be methane. And this aquamarine color of the planet in visible light is probably due to methane. This atmosphere is intensely cold. The temperatures vary depending on the altitude, but in the coldest parts of the troposphere, that is to say, the lowest and densest part of the atmosphere, they are near 50 Kelvin, below minus 200 degrees Celsius or below 350 degrees Fahrenheit. I made a story about the Earth atmosphere that explained the variations in temperature, up and down, due to the composition and density of the layers of gas. The atmosphere on Uranus is much lesser known, but it is well established that in the troposphere there are different layers of clouds. Where the pressure is lower, they seem to be made of ammonia, hydrogen and sulfur, whereas where the pressure is higher, they could be water clouds. And these different levels of the troposphere would have a highly complex structure, constantly moving, with strong winds and seasonal variations. Below the troposphere, density and temperature increase. Progressively, hydrogen and helium are less and less present, and we come closer to a kind of mantle made of these ices that give their names to this type of planet. Again, these are not actually solid ices. They probably were before the planet formed, but they are called ices because they are compounds that would be solid if they floated in space, like on a comet, or if they were at the surface of a rocky planet. This mantle represents the bulk of the planet's mass. In total, Uranus' mass is 14.5 times that of Earth. The gas envelope occupies a lot of space because it is not very dense, whereas this mantle is much denser. It represents more than 13 times the Earth's mass and about 90% of the whole planet. Given the conditions, the main components, which are thought to be water and ammonia, are believed to be in a state of dense and hot fluid. This fluid is sometimes called a water-ammonia ocean. By the way, you know what water is, but what is ammonia exactly? When hydrogen forms molecules with oxygen, you get water, as you know. Ammonia is a molecule that hydrogen forms with nitrogen. It is quite abundant in the solar system. There is some on Earth, but it can be found in much higher quantities on Mars, Jupiter, Saturn, and of course Uranus and Neptune, where it is an important component. On Earth, it is found only in trace quantities in nature, and often associated in salts with other elements like chloride or sulfur. But it plays a very important role in the cycle of life on our planet. It is a common waste of the feeding cycle of aquatic organisms, and it contributes to the nutritional needs of terrestrial organisms. Plants need it to grow, and it serves as a precursor to almost half of the world's food. Typically, fertilizers contain some. Now, returning to space, the mixture of water and ammonia has the particularity of freezing at a very low temperature. The melting point is as low as 173 Kelvin, which is minus 100 degrees Celsius, 100 degrees less than water alone. So in space, this water-ammonia mixture could act as an antifreeze and allow the existence of liquid internal oceans at temperatures far lower than it would be possible with water alone. But this is not a concern for Uranus, because where there is this water-ammonia mixture on the planet, the temperature is estimated to be much higher than that. Where the mantle begins, the temperature would be around 47 degrees Celsius, and the pressure 100 bar. That is to say, 100 times the atmospheric pressure at sea level on Earth. And then, traveling deeper into the mantle, temperature and pressure increase up to extremes at the center of the planet that are estimated to 8 million bars and a temperature of about 5,000 degrees. A hypothesis is that within the mantle, methane, which is also present, could be broken up under the constraints. Methane is hydrogen with carbon, and so pure carbon atoms, could condense into crystals of diamond that would rain through the mantle, almost like stones sinking in a lake, except it is not a lake of water, but of water and ammonia, with very high temperature and pressures that are superior to the deepest abyss on Earth. These rainfalls of diamonds may not be limited to Uranus. Theoretically, they could also happen inside Jupiter, Saturn, or Neptune. Another hypothesis is that at the basis of the mantle, where the core begins, there could be an ocean of liquid carbon. In this state it is called metallic carbon, because it conducts electricity. And yet another curiosity would be the presence of water at such high temperature and pressure that it becomes something called superionic water, or superionic ice. This is the same thing. What does it mean? The conditions are so extreme, and they actually cannot exist in nature on Earth, that the water molecules break apart and oxygen crystallizes. That is to say, it adopts a highly organized and repetitive structure, like a lattice. In between this lattice, hydrogen can float freely. The existence of this state, this phase of water, was only theoretical until it could be synthesized very recently, in 2019. In a laboratory, water was squeezed between two pieces of diamond and maintained at a very high pressure, and then blasted by a pulse of laser. In this experiment, the pressure was 1 million times atmospheric pressure. It defies imagination, but as we saw earlier, pressure inside Uranus could reach up to 8 million atmospheres, so it is theoretically possible in natural conditions on this planet. And the water was heated almost instantly with the laser to several thousand degrees, recreating the conditions that are believed to exist within the mantle of Uranus and Neptune too. As expected, oxygen and hydrogen in water molecules broke apart and oxygen crystallized. This phase of water is also called Ice 18. In a previous story about the moons of Jupiter, I told you about the different types of ice, of water, that are thought to exist depending on the conditions. Ice 18 is one more, and it is likely to exist in a stable state somewhere in the depth of ice giants, even though we are nowhere near the capacity of going there to take samples and check. After the mantle, the last part of the internal structure is the core, around which ices and gases aggregated during the formation process, or possibly where heavier elements migrated. We don't exactly know, as we saw when I told you about the formation history of the planet. This core is thought to be relatively small, around half the mass of Earth, and it would be made of rocks, of silicate, that is to say silicon and oxygen, and also metals. Now that we have quickly seen the inside, let's take a look at the periphery of the planet, because there are more things to see there. First, there are rings. They are not very visible and generally not represented on views of the planet, but 13 of them are known. The majority of them are very narrow, only a few kilometers or a few miles wide, and they are made of very dark particles that vary in size from microscopic to 1 or 2 feet. It is believed that these rings are younger than the planet. It could have been one or several moons that were shattered by impacts and left their matter all around the planet in orbit. Because there is a respectable number of moons around Uranus, we know 27 of them. So let's take a look at the largest one, Titania, which is also the 8th largest moon in the solar system. It is believed to have formed like the other moons of Uranus from a small accretion disk that surrounded the protoplanet in the early stages of the solar system. In its composition, Titania is very similar to several moons of Jupiter that we visited in our last space journey. Rock in the center and an envelope of water. It is unknown whether some of this water could be liquid under a crust of solid ice, but Titania is relatively small, much smaller than the Earth's moon. It may not have kept enough internal heat to have underground oceans, subsurface oceans, like Europa or Ganymede are suspected to have. At its surface, there appears to be a lot of canyons. This is not the kind of features that can be created by asteroid impacts. Canyons can appear due to plate tectonics, but Titania is too small for that, or because of erosion. But Titania doesn't really have an atmosphere with meteorological events that could provoke erosion. So a hypothesis is that long ago there was a liquid ocean on Titania under a layer of ice, may be kept liquid thanks to the presence of ammonia. As we saw before, it is a powerful antifreeze when mixed with water, because it freezes 100 degrees Celsius below water alone. And then, as Titania became colder as it cooled down, the subsurface ocean would have frozen. This would have made its volume increase, and it would have created these canyons at the surface because it would have broken the hard ice crust. Overall, Titania is an icy desert. It does not produce much internal heat. There is no atmosphere to retain heat, and it doesn't receive much sunlight due to the distance to the sun. But there are still variations of temperature due to seasons, and they are extremely long due to a particularity of Uranus. Uranus has the particularity to present its pole to the Sun, not its equator, like other planets. This could be due to a major collision in the distant past that would have tilted the planet. And the moons orbit around the equator of the planet, and Titania always presents the same face to the planet. It is tidally locked to it. So what it means in terms of seasons is that when Uranus is on one side of the Sun, Titania presents one of its poles to the Sun, and then the other pole. But as Uranus needs 84 years to complete one orbit, this means seasons on Titania last 42 years. One side is lighted for 42 years, whereas the other side is in the dark, and then they switch for another period of 42 years. Now let's resume our journey and go to our second destination, even farther away from Earth. Uranus is about 20 astronomical units from the Sun. Now we need to travel 10 astronomical units more to reach the orbit of Neptune, which, as we're going to see, is a near twin of Uranus, with a few differences. Neptune is so far away that it is invisible from Earth to the unaided eye, and this is why it was the first planet discovered not by observation, but by mathematical prediction. This happened in the first half of the 19th century. Uranus had been found and was now observed by telescopes, and its orbit was mapped. But something was off. There were unexpected changes in the orbit of Uranus that were not really explainable by the existence of other planets and the laws of gravitation. So either there was something wrong with the calculations, or there was something else, yet another unknown planet that influenced the orbit of Uranus. The position of a possible eighth planet was deduced from the perturbation of Uranus' orbit, and this ghost planet was tracked in the night sky until 1846, when it was found. In the following decades, several moons were also found around Neptune, starting with by far the largest one, Triton. We'll take a look at it a bit later. In terms of composition and structure and size, Uranus and Neptune are thought to be very similar. Envelope of hydrogen and helium, ices inside, that is to say water, ammonia, methane, to a lesser extent carbon dioxide. But in visible light, Neptune looks bluer, This is believed to be due to more methane in the upper layers of the atmosphere, and possibly another component that has not been fully identified. Another difference is that Neptune is a bit more massive than Uranus. It has 17 times the mass of Earth versus 14.5 times for Uranus. And it sounds counterintuitive, but it is also physically a bit smaller. This is due to its mass. It implies a bit more compression of its atmosphere. And in balance, it is a bit more matter in a bit less space. Another difference is the distance to the Sun. The two planets are 10 astronomical units away from each other, and this is a huge distance, about the same as the distance from the Sun to Saturn. And this means even less sunlight. Neptune is internally a bit hotter because of its bigger mass, so the temperature at the center is estimated at 5,400 Kelvin versus 5,000 for Uranus. But still, its atmosphere is one of the coldest places in the solar system. The temperature approaches 50 Kelvin, that's below 200 degrees Celsius, and only 50 degrees above absolute zero. Since its discovery, Neptune has completed only one orbit around the Sun. It takes 165 years, twice the time Uranus needs. And yet another difference is the intensity of meteorological activity compared with Uranus. Neptune's atmosphere is all but peaceful. There are giant storms constantly, a complex system of clouds, and the most powerful winds of the entire solar system. They blow constantly at more than 1,000 miles per hour in the upper atmosphere. This is believed to be a consequence of the differential in temperature between the core and the mantle, which are hotter than for Uranus, and the atmosphere, which is colder in its upper parts. And as you know, winds are the product of gas masses moving from one place to another, due to a differential in pressure and temperature. And on Neptune, these differentials are bigger. And so the planet looks constantly agitated by giant storms that have been observed since we have higher definition images. For a time there was a big dark spot comparable in nature to the Great Red Spot of Jupiter, and it was a storm. It finally disappeared, but more perturbations are constantly appearing and disappearing at the surface. Beyond Neptune begins a region called the Kuiper Belt, a very large region of the outer solar system, with millions and millions of small asteroids. Pluto, the dwarf planet, is one of these bodies. The limits of the Kuiper Belt have been set to between 30 astronomical units from the Sun, that is to say Neptune's orbit, and 55 astronomical units. And Neptune has a strong influence on this belt due to its gravitational pull. It has shaped its structure over time after hundreds of millions of years and millions of revolutions around the Sun. An example of that is the number of objects that are in orbital resonance with Neptune in the Kuiper Belt. I explained the concept in the story about Jupiter's moons because 3 of them are in orbital resonance. To summarize, it is when 2 or more objects on different orbits become locked by their respective influence on each other, and their revolutions happen in a stable ratio. In the example of Jupiter's moons, Every time Ganymede makes one orbit, Europa makes two, and Io makes four. So they are said to be in a 1-2-4 resonance. Neptune is in resonance with dozens of smaller bodies in the Kuiper belt, starting with Pluto. They are in a resonance of 2-3. That is to say, when Pluto makes 2 revolutions, Neptune makes 3. And there are also other ratios that have been found with other bodies: 3-4, 3-5, 2-5, 4-7. Over time, the Kuiper belt has become strongly influenced by Neptune, by its mass and orbit, in a way that is similar to the influence of Jupiter on the smaller asteroid belt, the one that is between the orbits of Mars and Jupiter. Neptune also has 40 known moons, most of them small, except one, Triton. Triton alone represents more than 99% of all objects orbiting Neptune. All the other moons together are not even 1%. So let's focus on Triton, because it has original elements, original aspects that make it different from most moons. The first one is that its orbit is retrograde. It orbits in the opposite sense to the rotation of Neptune. This is very rare for large moons in the solar system. Most of the time they are the opposite, prograde, meaning they follow the rotation of their planet. This is a strong clue that Triton did not form in the periphery of Neptune, but was captured later, possibly from the Kuiper belt, where it would have been considered a dwarf planet like Pluto if it was still in the belt. Triton is actually a bit larger than Pluto, and almost as large as the Earth's moon. So it is rather big, the 7th largest moon of the solar system. Its surface looks like it was renewed. This can be deducted from the density of impact craters. There are few, and this strongly suggests that if the moon can rejuvenate its surface, it is geologically active. That is to say that it has a differentiated structure with a core, a mantle, and a crust. That would be coherent with its size, and there seems to be 2 kinds of geological phenomena at the surface: cryovolcanism, that is to say, eruptions of warmer materials like water that surge and freeze at the surface, and also tectonic terrain that would release other materials from inside the moon, or that would let plates of crust move. This is how mountains and rifts can appear. How can a body of that size be captured, bearing in mind that distances are huge in the Kuiper belt? There are different possible mechanisms. In any case, it takes a very long time, and maybe millions of orbits around the Sun. Parts of Triton's orbit may have crossed or passed near Neptune's orbit, and bit by bit, the influence of Neptune would have slowed Triton down, so much that Triton's speed could have passed below escape velocity, allowing its capture by gravitation. The slowdown could also have been the consequence of a collision between Triton and an ancient moon of Neptune, now disappeared. Or yet another option is that Triton formed a binary system with another body, like Pluto and its biggest moon, Charon. The influence of Neptune on this system would have caused the system to interact in such a way that Triton would have been pushed to the orbit of Neptune and its partner expelled from the Kuiper belt, or even possibly from the solar system. We don't know, but it seems the arrival of Triton had catastrophic effects on the ancient moons of Neptune. It perturbated their orbits. There could have been collisions, and small moons could have been dispersed through gravitational interactions. When the system stabilized, Triton represented more than 99% of the mass in orbit around Neptune, the remainder being faint rings and small irregular moons. At its surface, in this region of intense cold, Triton is covered with a layer of frozen nitrogen. There could be an envelope of water, accounting for 15% to a third of the moon's mass, and below that, a mantle and a core of rock and metal. Like for many moons we have visited in our stories, there could be liquid water, a subsurface ocean, that could theoretically harbor life, but this is speculative, and it is already hard to imagine an expedition to Europa or Ganymede, which are 5 astronomical units away from the Sun. Triton is 6 times farther, at 30 astronomical units, so any manned mission to explore it directly is science fiction at this point. It takes a lot of patience to send probes to these regions of the solar system. All space missions take time, but this is really far. You remember we talked about the probe Voyager 2, that was the first to take close pictures of Uranus and Neptune. It was launched by NASA in 1977. It reached Jupiter in 1979, then Saturn in 1981. It took 5 years more, despite an acceleration, to reach Uranus in 1986. And still continuing to accelerate, Neptune was reached in 1989, 12 years after launch. Voyager 2 is still active, by the way, and now on a mission to explore interstellar space, 44 years after departure. The distance it has traveled is absolutely mind-blowing. When it reached Neptune 32 years ago, it was at 30 astronomical units from the Sun. Then it crossed the entire Kuiper belt, which ends at 55 astronomical units, and it exited the zone of influence of the solar system at 120 astronomical units. That was in 2018. Voyager 1, also conceived to reach interstellar space and launched almost at the same time, is also still operational and is now at more than 150 astronomical units from Earth. These 2 probes are by far the man-made objects that have traveled the farthest ever. But we have finished our little tour to ice giants for tonight. If you wish to go to more distant destinations, I'll put the links to stories about exoplanets and galaxies in the description. For now, you can let go and fall asleep, remembering that we really are small and not that important in the grand scheme of the universe, of which we have traveled only a tiny portion tonight. Sleep well, sweet dreams, au revoir.